Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the NPTEL course on groundwater hydrology and management, week 1, lecture 2. We are still very early in the lecture series for groundwater hydrology and management. So the first week, as I mentioned in my breakup slides for the week, we would be looking at what will be offered in the following course, and also stressing on the importance of groundwater. Groundwater is a very valuable source, but unless we understand why and why is it used so much in India, it will be difficult to manage it properly. So the understanding first comes, followed that we will take you through the management part. The hydrological cycle would be explained in most civil engineering earth science courses. In general, there are multiple components, and this is the overall hydrological cycle. Let me explain the hydrological cycle for those beginners. It is a cycle which can start from any point and then be cyclic in nature. So for ease of teaching it and understanding, let us start from the atmosphere, which is the clouds. So in the atmosphere, we have clouds. And clouds have water vapor which is being condensed. Once it condenses, especially after cooling down and multiple other processes, what happens? You get precipitation. Precipitation can come as ice, snow, and glaciers. It can also come as rainfall. Since in India, most regions receive rainfall rather than snow, we will focus on groundwater hydrology estimations based on rainfall. Okay, I will mention some other things. For example, Ganges River gets rainfall plus snow melt, but we'll focus on rainfall for the most part of the course. Some part of your ice and snow melts down and joins with your rainfall and then converts into your streams and rivers discharge, etc. So you could see water falling on the slopes of the mountains, and then it collects along the stream network and flows down into the freshwater lakes and rivers. After that, it can also flow down. If there's no lakes and rivers, it can also flow down to the oceans, seas, and bays. This creates a loop from the atmosphere to the ocean, where again it gets evaporated back into the atmosphere. But before that, there are very important parts in the hydrological cycle, which is important to understand the groundwater hydrology. This figure is a very informative figure which has been widely used from USGS. Even in government records, we can find this image. Those who would like to have more information can go to this website and read about the different cycles, but I would explain most important ones here. So once you have your runoff, which is the conversion of precipitation into water, running water, you get it infiltrated and goes into the groundwater. Okay, so this component, what you see is a process higher than the precipitation, because once precipitation occurs is only one process. The higher process is the water has to get down into the ground through infiltration. And once infiltration happens, there is relocation of water into different groundwater compartments, which we will discuss in the future parts of the course. So water flows through as groundwater, not like a river, but it flows through pores and soil and solid materials, and then comes out into the surface water storages, fresh water, springs, seepage, etc. Part of it goes into the deep aquifers and then stays there, deep groundwater zones. But most importantly, it comes back to the ocean. So even the groundwater zone here, the deep ones, you can see water can come out and seep into the oceans. So somewhere your salty water or saline water is evaporated, only the water vapor goes up, and while it goes up, it cools down, forms clouds. Further condensation leads to rainfall, which is fresh water. Okay, you start with saline water, you end up with fresh water. Then what happens? Your fresh water goes through multiple processes and then comes back to the ocean. For groundwater, it goes to different groundwater components and either gets stored or flows through into the ocean. So now you have water coming back to the ocean. The cycle doesn't stop. Evaporation happens again. Some of the groundwater is taken by plants and goes as evapotranspiration. We'll go through all this in detail, but just I'm telling you in the hydrological cycle, where does groundwater play a role? So either it can get stored, it can flow, or it can be taken up by plants and then mixes into the ocean. After it mixes into the ocean, it can come back to the atmosphere as clouds, precipitation. Again, the cycle goes on and on. And this is driven by the sun. So you see the sun here, it is very aptly placed because if the sun doesn't work, if sun shuts down, plant life doesn't work, there's no transpiration, there is no evaporation from open surfaces, most of it would be gone. And so your cycle, which is your rain cycle, will not happen. Too much of that is also bad, which is what we are seeing in climate change scenarios, that too much heat or warming can increase your evaporation, thereby increasing floods and droughts. Droughts because there's no rain, and floods because too much rain can come at a single point. So we've seen the different components, and for groundwater, it's very important to understand there is groundwater storage, there's groundwater flow, and then groundwater mixing into the ocean back. So this is an introduction for a hydrological cycle. We will get back into the groundwater hydrology, which is a focused hydrological cycle within the overall hydrological cycle. So what you see is an overall hydrological cycle. Let's see why it is very important to manage groundwater. Okay. First, let's take a step back and understand overall water resource management. Where is our water coming from? Where is it stored? Okay, so we'll answer these questions now. Overall, all of the water, if you take in the planet and do an analysis, this is the results. Out of the 100% of water that we have on the planet, 97.5% is in oceans, which means it is either saline or not usable, not accessible. Because how do you access water from the Pacific Ocean? Are you going to put a big pipe and then pump it out? No. First, the energy, etc. is there. But most importantly, the quality of water, which is saline, salty, you can't use it. Then comes this 2.5%, which is fresh water. So out of the 97.5 or 100%, 97.5 is salty water in oceans, 2.5 is fresh water. Not all this fresh water is usable. So now of the 100% of fresh water, okay, so this circle is 100% of the 2.5. So don't think it's another 100%. So of the fresh water, ice caps and glaciers have 79%, which means on top of the Himalayas, the big Alps, and all the big snow regions, Finland, Iceland, etc. And then you have your glaciers, Antarctic, Arctics. So you have all this together combining to be around 79%, which leaves us to 21% of available freshwater, easily available freshwater, or relatively easily. Of the 21%, only 1% is easily accessible surface water, whereas the remaining 20% is groundwater. Okay, so now comes the big picture. In the fresh water, the accessible water is groundwater, the biggest component, because you're not going to sit and melt ice caps and glaciers. There are some countries which are thinking of taking glacier water for drinking, but how do you sustain that, right? So, but groundwater is kind of decentralized. It is everywhere, so you could easily access it and then take it out. But is it sustainable is the question. So that's what this whole course is about. So the 1%, which is easily accessible, is in the form of lakes, soil moisture, atmospheric pressure, rivers, water within living organisms. So whatever you see as big rivers, Ganges, Indus, Brahmaputra, the Kaveri, etc., all this is not only for India, for the world. If you combine all the big rivers, all the lakes, dams, etc., which are storing water, it is only within the 1% of fresh water. So how much percent will it be on the total? It is such a very small portion. Okay. So of the water resources, if your demand is high for fresh water, what do? You will have to eventually go for groundwater because it is 20% of your fresh water. Okay. So mostly water is salty in the oceans. Even fresh water is locked. For example, in glaciers, ice caps, snow, it is locked. It is not easily accessible. Easily accessible is a very small portion, and of the portion, groundwater ranks highest, which is 20% of fresh water. Not all 20% can be easily extracted because sometimes groundwater gets locked into the soil, the rock materials. You can leave that part. But science and technology has increased the access to groundwater. Let's see another record. Similar percentages by a different study. And you will understand that of the fresh water, around 96.5% is in ocean, seas, and bays. Ice caps, glaciers, permanent snow is 1.74. So 1.69 is the actual percentage of groundwater of the total. Okay. Of that, as I said, fresh groundwater is only 0.76, whereas 0.93 is saline groundwater. You cannot use it. It's locked, either locked or it's too salty. You would have heard that people say groundwater is color, it has a color, it has a smell, or it has a salty taste. It's because it is from the regional groundwater aquifer or from the parent material rock. The rock characteristics will come into the water. Okay. Either way, if you look in the previous figure, you have, if you do the calculations, around 0.5% of your total fresh water, okay, is in the form of ice caps, glaciers, etc., etc. If you take just the groundwater, it equates to roughly around 0.05% of the total water in the world. Okay. As per that estimate. Here it is 0.76, and even the 0.76 you have around some water which is fresh but not accessible. Okay, coming back down, soil moisture, ground ice, permafrost, lakes, etc. You can see that the percentage is very small, 0.007, 0.006 in your lakes and atmosphere, etc. Rivers is only 0.0002. Okay, biological water is 0.0001, which is in our bodies, the animals, etc. So the driving note here is the groundwater is the next biggest available water resource on the planet for fresh water, which is easily accessible. So the first would be your big lakes, ice caps, glaciers, melts, and snows, but it's not accessible. So if you do the accessible calculation, then groundwater ranks high above your lakes, rivers, etc., as the biggest contributor for fresh water or biggest source for storing fresh water. On this note, so we have understood where the water is, how the bifurcation is for groundwater. On this note, the water stress looking at. Let's take the WRI report in 2013. You could see that baseline water stress is pretty high in India. So most course material would be focusing on India because we would like to produce more groundwater managing professionals, capacity in India. So the course would be tailor-made for Indian regions a lot. So if you look at India here, the subcontinent, you could see a big red color, which shows that the water stress is going to be high and very high, extremely high, right? So is this good for India? No. And there are multiple reasons why this is happening, why you see the color pattern you have, because some regions are low, some regions are arid and low water use, so no data, etc., etc. But most of India is in the red color, which is kind of concerning. Why is this stress different between different countries? You can see US, China, Australia have better water resources, whereas the developing nations do not have that much water, right? Which means high stress is there. Why is it? It is important to understand the disparity in water to better understand this question of differences in water stress across the globe. Let's analyze the competing water resource uses. You have domestic use, you have industrial and agriculture. There are multiple more uses, but let's focus on the key high water consuming sectors. One is domestic, what we drink, what we use for bathing, clothing, washing, your maintenance, sanitation, etc. Then you have your industrial for industrial purposes, and then agriculture for your farming, livelihood options, etc. What you see here is of the world, almost 70% of the water is used for agriculture, whereas you have 22% used for industries and 8% used for domestic. This is the world average. So if you give the world 100 liters of water, 70 liters is going to be used for agriculture, 22% would be used for industries, whereas 8% would be used for domestic. So it's a good standard. If you come to low and middle income countries, the 8% is the same. So we are almost on average to the world average. But then the industrial demand is less, only 10%. And agriculture demand is more, 82%. So most of the water is spent on agriculture in developing and lower income countries, not only for them, because they are going to export the food to developed countries. For example, Vietnam, Philippines, Thailand can grow rice for the entire planet and send it to Russia, US, the Europe countries, etc. Right? So that water that effectively can be used for industry is being more consumed for agriculture in low and in lower income countries, India included. If you come to the high income countries, they don't use that much water for agriculture, only 30%. And that too, it will be for very specific crops like your almonds in US, sugarcane, and then you have corn, which are giving some value for the industries also, brewing industries and other industries. Table grapes and other wine vineyards. So those kind of industry related agriculture they have. Most of the other food is kind of imported from other countries. They export very less also. So 59% is used for industry. So now you could see that high income countries are smart in using the water for industry, which can create more jobs, which can create more income for the country. Whereas low and mid-income countries use most of the water for agriculture, which is a sole purpose of feeding the public. And it has very less profits compared to the industry. So the same water, you can look at how a high income country uses. For example, Singapore would buy all the food materials, crops, rice, chicken, anything related to food. They can source it from neighboring countries like Malaysia. And they can put all their water into industries or banks and those kind of things. Whereas the agricultural countries, low income mid countries are keeping low income because they don't use their water for high end products. I'm not saying that these countries should also get into industries. What I'm saying is the profit and the value of agriculture is kind of low. And that is why low and mid income countries become low, because either way you still have to eat, right? So if you have an industry which can give good water related profits, why can agriculture become that too? So we need to think in those terms to bring up the nation, because India itself is an agricultural nation. If you use now this understanding in this figure, clearly see wherever the red marks are the regions where agriculture is predominant. For example, even the US, this is where you have your almonds and orchards growing. And almonds are exported to every country, including India. And then you have your rice and other cultivations in the subcontinent, Southeast Asian countries. And then you have agriculture happening in some parts here. Okay, and Middle East is always highly stressful water because of the high, temperature and desert kind of an ecosystem. So we cannot compare that. Not much agriculture here, but most agricultural countries around here, you could see very high stress because most of the water is used for agriculture, not industries, and they do not get much profit out of it. So that's why their income is still low. Moving on, within India also, let's now take a case study for within India. 54% of India faces high and extremely high water stress. Same report, if you look at just for India, you could find astonishingly that above 50% of India, let's take the population, more than 500 million people are going to be under high or extremely high water stress conditions. This is not a good news, because we need to push further in conserving water. And if you look at where this is more prevalent, you could see mostly the states with high agricultural activities, Punjab, Haryana, and also the desert ecosystem kind of regions, and mostly your rice belts in the south. So there is a big need to push for better water management resources. And this is also the reason why your groundwater is being abused. So this is a report from the Central Groundwater Board, the very recent one, which dates to 2017, and they've categorized the blocks in India where water depletion is pretty high. We will not get into the details of how it's characterized because we'll have different lectures. For now, let's understand that overexploited and critical are very, very concerning, especially the red color. And if you look at it, it is almost following your water stress conditions, which means groundwater is also being stressed in these regions. Okay, and along the regions where there's tremendous amount of pumping for agriculture, there's not much pumping for industries. There are one or two blocks you would find. So one block in maybe Bangalore, for urban Chennai, you can find a lot of water being used, but most of the water is used for agriculture. So if you see a combination of blocks like this, then that means there is high demand on groundwater and they're extracting more than they should, which is over exploiting. On this note, I think it is clear that we should understand where groundwater hydrology comes into picture from the overall hydrology. We've also understood where groundwater fits in the overall water budget of the planet. Okay, there might be different estimates, but still it's less than 1% of the total water in the planet is groundwater, less than 1%. And within that 1%, some are not accessible. So there's still a very small portion of accessible groundwater. However small it is the biggest easily accessible freshwater resource in the world. So on one hand, it is already less. On the other hand, it is the biggest source easily accessible. And on the third, it is accessed everywhere for agriculture. Because of the ease in accessing groundwater through pumps and science and technology, a lot of people have started to overuse the groundwater. So this forms the base of this course, why groundwater has to be taken away from hydrology and studied in focus. So this discussion, what we had now, forms the basis for it. So we would have to look at groundwater in a separate lens And to understand that, how to manage it, it is very important to understand the physics behind groundwater, the equations behind it, and put it on track for better management activities in the years to come. The multiple agencies that work on groundwater management and groundwater monitoring, but there is a big need on local hands-on participation so that we could all combine, collectively use it on the same way, all combine and collectively manage groundwater. With this, I would like to conclude today's lecture. Thank you.